Let us talk about this popular problem called n-queen problem. We are given a number n. We need to consider n cross n chessboard and we need to place n queens on this chessboard such that no two queens attack each other. Please note that a queen can move horizontally anywhere, vertically anywhere, diagonally anywhere, right? So if your queen is placed here, then you cannot place any other queen in any of these locations, right? They all are blocked by this queen, right? So we need to place queens such that no two queens come in range of each other. They do not attack each other. For n equal to 4, we can place 4 queens on a 4 cross 4 chessboard. That is why our answer is yes. And this is one possible arrangement for placing the queen. First queen is placed here, first row, third column. Second queen is placed here, third here, and fourth here. Please note that there are more arrangements where queens do not attack each other. We just need to print one of them, and this is one possible output. For n equal to 3, it's not possible to place 3 queens on a 3 cross 3 chessboard such that they do not attack each other. You can try different permutations and you will figure out that it's not possible to place the 3 queens. For n equal to 5, the answer is yes, we can place the queens, and this is one possible arrangement. One queen is here, second is here, third is here, fourth is here, and fifth is here. You can notice that no two queens are attacking each other in this configuration and this configuration. Now please pause this video and write a function that takes n as a parameter. This function should return Boolean value. It returns true if there exists a solution, and it also prints the solution in that case, if there exists a solution. If there does not exist a solution, then this solution should return false. Let us now talk about the solution. A super naive solution is to generate n square Cn possible configurations. We have n cross n chessboard and we have n queens to place on this n cross n chessboard. So there are n square Cn possible ways to place the n queens on this. For example, if n is 4, then we have 16 C4 configurations where we can place the queens, 16 C4 possible configurations. So a super simple solution is to generate all the configurations one by one. For every configuration, check if it is a valid configuration or not, if the queens are attacking each other or not. And if you find a configuration, you return true at that moment and you print that particular configuration. This is super naive solution, very expensive solution. A better naive solution is based on the fact that every queen is going to get placed into a different row and in a different column. So what we do is we generate all possible permutations of numbers from 0 to n minus 1. For example, if n is 4, we generate all possible permutations of 0, 1, 2, 3, right? And every permutation represents row indexes in different columns. Let's see this example. This is a permutation 1032. These are row numbers in columns from 1 to 4. So first queen is placed in column 1 at row number 1. The second queen is placed in column 2 and row number 0. So column numbers are always 0 to 3, right? In every permutation, these are just row numbers. The third queen is placed at row index 3. The fourth queen is placed at row index 2. So in the naive solution, we mainly generate all possible permutations of numbers from 0 to n minus 1. Then we iterate through all these permutations, and for every permutation, we check which one is valid or not. In which permutation queens are not attacking each other, all queens are not attacking each other, and we print that particular permutation or the solution corresponding to that permutation. We place the first queen at column 0, and in column 0 we have 4 choices for row number. So there are different 4 children for the root for different row numbers in the column 0. Row number can be 0, 1, 2, 3, right? Once you have placed a queen, then you place the second queen. For second queen, you have 3 choices. You have choice for row 1, row 2 or row 3 because row 0 has been occupied by the first queen. So this particular level in this tree represents different choices for column 1, and this particular level represents the choices in column 2 once you have made a choice in column 1, right? So once you made this choice, you have 3 choices for column 2. Once you made this choice, you have 3 choices for column 2. This particular level represents the choices for column 3 or column at index 2. And this particular level represents the choices for column at index 3. This is how our recursion tree is. So we are going to generate this recursion tree, and then we are going to generate all the permutations, and then we are going to check which one is valid. Let us now talk about the backtracking solution. In backtracking solution also, we are going to place the queens one by one, but we are not going to follow the whole recursion tree. What we are going to do is, as soon as we place a queen and we realize that this placement is not going to lead to any solution, we do not further go down in that path. And that way we cut down the recursion tree leading or starting from that particular path, right? And this is the optimization we get in backtracking solution. Not only this, as soon as we find a solution, we stop our recursion tree at that point. So we are not going to do lots of recursion trees in this particular whole tree. Let's see how does this backtracking solution begin. So it's going to begin like normal recursive solution that we just talked about. We place the first queen in the first column, right? So these are 4 choices for first column. And in the first column, we have made a choice to place it at row 0, right? So we place the first queen here. Now we are placing the second queen in row 1. So we place the second queen in second column. So this represents the second column, right? So we place the second queen here in this particular second column at row index 1. Now we see that there is a clash between these 2 queens. So we know this part is never going to lead to a solution. So we cut down this whole recursion tree, right? So in backtracking, we have this function called isSafe that we generally use. So when we call isSafe, after placing this queen, we realize that this is not going to lead to the solution. We stop here. We do not call any of these recursion parts, and we immediately return false from there. Now the parent call is going to place the queen at different place here, right? It's going to place the queen here now. So this placement works fine. So we proceed with this recursion. Now we place the third queen here at index 0 to 1, right? So 0 to 1, here we place the queen. And when we place the queen here, we again see that this is not going to lead to the solution because they are going to attack each other. So we cut down this recursion also. Now we go back here, and what we do is we place the queen now at different location, which is 0 to 3, right? So when you place 0 to 3, again they are clashing. So you cut down this part. So you have tried everything with this placement and none of these solutions are working. So you backtrack from this point also. So you try placing the queen here at this third, because both of these recursive calls have returned false. So this is going to return false to the parent, and then parent is going to try the queen at this particular row number in the second column, right? And after placing the queen here, it tries with the third column and it places the queen, the third queen here at this index, right? And after placing the queen here, it has this choice for the fourth queen, but this does not lead to a solution because they're clashing each other. So this returns false to its parent, and then parent returns false to its parent, and then it realizes that this is not going to work. So it tries the next possible place for the queen number in column 3, right? In the third column or index 2. And when it places the queen here, it again clashes with the previous queen, right? So this particular recursion tree is also cut down, right? We do not go to this. So we did not get any solution after placing the queen at this particular place. So when we placed the queen here, we tried 3 possibilities and we did not get any solution from any of these 3 possibilities. Then we are going to place the first queen at second row or row at index 1. And after that, we again try placing the queens. So we try placing the second column queen at row 0, right? So we place queen here. And this is going to clash. So we cut down this whole recursion tree, right? Now we try placing the queen at this index 1, 2, right? Second queen here at row number 2. So this is also clashing. So we cut down this whole recursion. Now we place the queen 1, 3. And this is not clashing. 1, 3 is not clashing. So we try going down here and place the third queen at 0. So place the queen at 0. Now we place the fourth queen at 2, and we got a solution. None of these queens are clashing, so this is our solution. Once we get the solution from here, we do not go any of the recursions in any of the remaining recursions, and we return the solution from here as 1302 as our possible permutation, possible solution of this problem. In case we want to print out all possible answers, like not only this answer, we want to print out all the possible configurations of queen which do not attack each other, we can proceed further in this recursion and we can print all the possible configurations like this configuration, right? So this is the idea of backtracking solution. We follow the normal recursive process like generating all permutations, but what we do in this solution, as soon as we find that this path is not going to lead to the solution, we cut down that recursion. That way we save a lot of work. We did not execute this whole recursion tree because we realized that 0, 1 is clash, right? So we did not go down and made these two recursive calls. And you can imagine what will happen when n is big number. For example, n is 8 or 16. You're going to cut down bigger recursion trees, and backtracking is going to save time in this particular solution. Let us now talk about implementation of the backtracking algorithm. In this implementation, we mainly have 3 functions. This function is mainly a wrapper over this function. And what it does, it uses the return value of this function. If this function returns false, then it simply returns false. And if it returns true, then it prints the result and returns true. And what is our result? Result is the board matrix. So we are maintaining a board matrix of size n cross n that we showed in the initial examples. And if there exists a solution, then we are going to place 1, 1, 1 in the places where we are going to place the queen. And we initialize this board matrix as false values or 0 values, right? So this is our only wrapper function, which calls this function with column equal to 0, right? Because this is the first column where we put the queen. Then we have isSafe function. This isSafe function mainly checks whether placing a queen at given row or at given column is safe or not, right? So it takes row and column as parameters and returns true if you can safely place the queen at this row and column, and returns false if you cannot safely place. So how does it check whether you can safely place or not? It mainly checks with the previously placed queens. If the current location clashes with any of the previous placed queen, then it returns false, otherwise it returns true. And how does it check if the queen clashes with any of the previously placed queens? It checks for the current row. Have we already placed any queen in the current row? Please note that we are anyways placing queens in different columns, so we do not need to check for column. We only check for the previously placed queens in the current row, and we check in the previous columns because we have not placed any queen from column to last column, right? From this column to last column. Now we check in the upper diagonal, right? We begin with row and column, we do I minus minus, j minus minus, so we check in the upper diagonal, this side. So if you're placing a queen here, you will check these two, right? By doing I minus minus and j minus minus. Then we check in the lower diagonal. So if you're placing a queen here, you will check the lower diagonal. If you're placing here, then you will check these two, right? By doing I plus plus, increment the row and decrement the column at the same time, at same speed, and that is how you reach the lower diagonal. So if you have any queen already placed in any of the 3 things, then you return false, and if there is no queen, then you return true. That's what isSafe function does. Let's now talk about our main function. This is our main recursive function that takes column as an argument, and initially we pass column as 0 to it. So what it does, the first thing it checks if column is n. If column is n, that means you have already placed all the queens, right? Column goes from 0 to n minus 1. And if you're calling for n, it means you keep on incrementing the column, and at the end, if it becomes n, then you say everything plays. So you return true. And if column is not n, then it tries placing the queen in different rows of current column, right? It tries placing the queen at row 0, then row 1, then row 2, then row 3, right? And for every trial that it does, it first calls the isSafe function. Can we place the queen in this particular row? If we can place, then it places the queen, and after placing the queen, it calls recursively for column plus 1. And if this recursive call returns true, then it returns true. And if this recursive call returns false, then it removes the queen from this particular place, and that's what is called backtracking, right? And it continues with the next iteration by placing the queen in the next row. So this is how this recursive function works. This is the recursive call we have here. It calls for column plus 1. And at the end, if you've tried everything, then it's going to return false, right? Because we tried anything and nothing returned true. So this is the recursion tree for this recursive function. Other functions are really simple. The main part is this. So we've drawn the recursion tree for this particular function. And initially, our chessboard is empty. We place the first queen in the first column and we try placing it in different rows. We begin with row 0, right? So we place this queen in row 0. The 0 actually indicates the row number, right? So we place the queen in row 0. After placing the queen in row 0, what you do? You try placing the next queen in different places, right? So you recursively call for the next column. When you recursively call for the next column call goes into this iteration, right? You call for column plus 1, which is column equal to 1. So when you call for column plus 1, it does not go into this if part, it begins execution from this loop. So this call tries placing the queen in different rows of second column or column equal to 1. So it begins with row equal to 0 and SA function for row equal to 0 obviously returns false because there is already a queen in row 0. Then it tries row 1. SA function again returns false because there is diagonally a queen placed. Then it tries for row equal to 2 and this is where SA function does not return false. So it places the queen at row equal to 2. And after placing this, it recursively calls for third column or column equal to 2. And this also begins execution from this line. And column is not n, so it goes here and it tries placing the queen in different rows of the third column. So placing the queen here would return false. A safe would return false because there is already a queen. A safe call for this will also return false. A safe call for this will also return false. A safe for this also returns false. So queen cannot be placed in any of the rows. So this recursive call returns false. So when this recursive call returns false, this recursive call backtracks and tries the next row, right? So backtracking happens, the queen is removed from here and then queen is placed here, right, in the next row. And once the queen is placed here, you again recursively call for the next column and execution again begins from the first line. So this time again you try placing the queen everywhere. So you try placing the queen here, is safe returns false. Here is safe returns true. We can place the queen here. And after we have placed the queen here, we call for the next column. When we call for the next column, recursion again begins from here and tries placing the queen different places. So here it is safe false, is safe false, is safe false because there is already a queen in the upper diagonal. Here also is safe false. So is safe returns false for all these 4 places. So you again backtrack. You go back and you see that you already tried all the rows in this particular column. It means you do not have any solution from here. So what you do is you remove the queen from here itself, right? What you do now, you place the queen in row equal to 1 or second row, right? First queen in the second row. Now you recursively call for second column or column equal to 1. And when you call, the recursive function begins execution from here, right? And tries placing the queen at all places. So when it places queen here, is safe returns false, is safe returns false, is safe returns false, and is safe returns true for this. So you place the queen here, right? And now you make a recursive call for third column. So when you try placing the queen here, is safe returns true. You can place the queen here. So you place the queen here. And after placing the queen here, you call for the next column. And next column call will try placing the queen here. Is safe will return false. Is safe will return false. And it places the queen here, right? So it places the queen here and calls for column plus 1. And when you call for column plus 1, what happens? Column becomes n. And at this point, you return true. So you have placed all the queens. That's how your all recursive calls, parent calls, they also return true. And your final board has these values as 1. So you can print the board as output of this program. So we have talked about a backtracking solution, and you can notice that how small the recursion tree is, how much less work we are doing here compared to the whole recursion tree that we drew when we were talking about the naive solution. because backtracking simply cuts down the recursion whenever it sees that the solution is not feasible here.